So today we'll be doing what is called as a dominant strategy equilibrium. So till now what we have seen is just how to represent games and what are certain assumptions that we have in the game. But we don't really know what the outcome of a game is, or we have not really defined what an outcome means. So today we'll be defining at least one of the outcomes, which is dominant strategy equilibrium. When I say outcome, what I'm looking for is an equilibrium, a notion of an equilibrium in a particular game. And there are many notions of that. One of them is dominant strategy equilibrium. And if time permits, we'll also look at what is Nash equilibrium. So I hope online I'm audible and everything is fine, right? The slides are visible. Okay. Speak up, okay? I won't know if you raise your hands and things like that. Okay, a brief recap. What we saw what is a strategic form. Strategic form has three main components: number of agents, actions, and strategies and utilities. And then we saw what are utilities and how we establish what a well-defined utility is through utility theory, given by von Neumann and Morgenstern. And then we saw what are rational players, what are intelligent players, what is common knowledge, and how are these helpful in game theory, how these assumptions are useful to set up these games. And then we saw what dominant strategies are in the last. So today we'll see what is a dominant strategy equilibrium. We'll see what is iterative dominance. And if time permits, we'll also see what is Nash equilibrium. These are the references for today's lecture. So this is Nalhari's book that we are anyway following. And the other is, this is a very dense book by Tim Garden, Norm Nissan, and there are many more authors here in this book actually. Each chapter is written by different authors who have expertise in that particular field. And what I have covered till now is not even, I mean, I've not even started any part from this book. There's just four subsections of my chapter, and that's what I've covered till now. The exercises of this particular book are quite challenging. If anybody is wanting to work out something very tough, you could take up the exercises from this book. Okay, so a brief recap of what dominant strategies are. This is Prisoner's Dilemma. For the 100th time, I'm probably describing what Prisoner's Dilemma is. There are two agents, and each of these agents have two strategies: confess or not to confess. And because of that, they get certain utilities that is defined. So do players have any dominant strategies in Prisoner's Dilemma? Is it? What is a dominant strategy?
To confess.
That's the dominant. But in general, what is a dominant strategy? The dominant strategy is, irrespective of what the other agent is playing, what is my best strategy? Does it exist? So, for example, in this case, if I have to look at player 1 or the rogue player, that is player A, confessing, if the other agent is confessing, so we are in this part of the matrix. We're in this part of the matrix. If the other agent is confessing is giving me -5, and not confessing is giving me -10. So I should confess. Similarly, if I look for the other thing, when the other agent is not confessing is giving me -1, and not confessing is giving me -2. So no matter what the other agent is doing, it's always better for me to confess. Which is why confessing is a dominant strategy for player 1. In fact, it is strictly better to confess. Why? Because -5 is strictly greater than -10, -1 is strictly greater than -2. So it's a strict, strongly dominant strategy. So what is a strongly dominant strategy? This is the proper definition of strongly dominant strategy. If I am given a strategic form game with these components, a strategy SI star is said to be a strongly dominant strategy for a particular I if it dominates every other strategy. It strongly dominates every other strategy. By which I mean that utility that I get from playing SI star, then so everybody else is playing S minus I, is strictly greater than any other strategy that I play, given that every other player is playing S minus. So here there is a strict inequality. So this strict inequality sort of tells me if the strategy is strongly dominant or not. Okay. And this must be true for every strategy that the other players are playing. So for every strategy that the player B was playing, that was either to confess or not confess, for me, confessing was the best strategy, was a strongly dominant strategy, as opposed to not confess, as opposed to any other strategy that I had. I hope the definition is clear for what is a strongly dominant strategy. So if I slightly change the prisoner's dilemma, what is does this have a strongly dominant strategy now? For any of the players? Strongly dominant. Is it strongly dominant? I have changed the numbers a bit. So how do you see? You again see for each of the, you fix the other player strategy. If we fix C, then I'm strictly getting better by confessing, the row player. But if I fix NC, I'm not getting a strictly better payoff. Both confessing and not confessing are giving me minus. So this is not a strongly dominant strategy. Similarly, for the column player also you can argue. If I fix row player strategy, then both not confessing and confessing are giving me minus. Now you have to see the second. So this is not a strictly, but what is this? This is actually called as a just a dominant strategy or weakly dominant strategy. So what is the definition of a weakly dominant strategy? See, given a game, a strategic form game, a strategy SI star is said to be weakly dominant strategy for a player I if it weakly dominates every other strategy. So I have the same definition, just that I have a greater than equal to sign here. So it has to be either greater or at least as good as any other strategy, given that everybody else is playing some strategy S minus I, and there must be strict inequality for at least one of the others. So when the other agent was playing, so in the previous case, in the example that I had, so for confessing, it was strict inequality. When the other agent was confessing, for me, confessing is strictly better. But when the other agent is not confessing, it is as good. Right? So for at least one of these strategies of the other agent, for at least one of the S minus I, for at least one of the S minus I, there should be a strict inequality. And for the rest, it could be equal or then it is a weakly dominant strategy.
So like if it was equal everywhere, then it would be weakly dominant.
It won't be weakly. It will still be weak. So there is one more thing called very weakly dominant strategy. I'll just, yeah, that's what it is. Okay. Now, so that's strict inequality for at least one S minus I. I hope this is clear. This is weakly dominant strategy. Now there is one more thing which is very weakly dominant strategy, wherein I let go of even this constraint. If there are two strategies that give me exactly the same utilities, right? Both of them are very weakly dominant strategies. Now, the other way, so still what we have seen right now is strongly dominant, weakly dominant, and very weakly dominant strategies. But there could be strategies which are dominated, right? A strategy which is strictly worse off for me. I should not play that strategy at all, because there exists at least one other strategy which is giving me better utility than this particular strategy. Then such a strategy is a strongly dominated strategy. So there exists some other strategy which is giving me strictly better utility for all possible strategies that the other players are playing. Then this particular strategy, SI, is a strongly dominated strategy. The strongly dominated strategy. Similarly, here also we'll have weakly dominated and very weakly dominated strategy. So when I say weakly dominated strategy, so there exists one more strategy which is giving me better utility and at least as much utility for the other players, but there should exist one strategy for every other player, wherein I'm getting strictly better utility by playing SI dash, which is why SI is dominated by. Right? So SI is not a good strategy for me to play, because there is at least one other strategy which is giving me, if not better, at least as much. And very weakly means you just remove this other constraint of with strict inequality. There are two strategies which are giving me exactly same utilities, and in that case they are very weakly dominant. So I think this will be clearer with an example. So I've just shown row player utilities here. There's no column player here. But can you tell me in both of these games, separate games, what are the strongly dominated, dominant, all the possible combinations? So first let me ask it. So is there any strongly dominant strategy in either of these matrices? What is a strongly dominant strategy?
First matrix, capital A.
First matrix, capital A is a strongly dominant strategy? Is it? Why? But there is B, which is also giving him almost same, right? So here what is S minus I? Here we are only looking at row player. Right? So SI could be A or B or C. S minus I could be small a, small b, and small c. Right. So I want a strategy. When is a strategy strongly dominant strategy? Then for all S minus I, it is giving me strictly better utility. Right. So if S minus I is A, there is a strategy which is giving me strictly better, which is capital A. But if it is S minus I is B, there is no strategy which is giving me strictly better than the other, right? Similarly for S minus I is equal to 6. So in this case, I don't really have a strongly dominant strategy. Had there been 6 here, all of them, then that would be a strongly dominant strategy. What about in this matrix? Is there any strongly dominant strategy?
No.
Is it clear to everyone? Do you have any doubts about strongly dominant strategy? Okay. Are there any weakly dominant strategies here?
Yes.
Which would be the weakly dominant strategy in this matrix? Capital A is the weakly dominant strategy. Because
it is strictly greater than C. At least one has
in A it is strictly greater than the others. When S minus I is equal to A, it is strictly greater. For other, it is at least as good. Which is why it's a weakly dominant strategy. And what about here? Are there any weakly dominant strategies here? Because yeah. Why are there no weakly dominant strategies?
Because it doesn't have a strictly equality.
It does not have a strict unique form. So for every S minus I, there are two strategies which are giving me exactly same utility. So there is no strict for any one of the strategies that the other player is. Therefore, I do not have any weakly dominance. So expect a lot of questions from this. To make questions. So be thorough in this. What about very weakly dominant?
Second matrix.
First.
Because, and all weakly dominant strategies are also very weakly dominant.
Very good. So all weakly dominant, so very weakly dominant strategies is something where we are even relaxing the definition further. So every weakly dominant strategy is also a very weakly dominant. Like that, every strongly dominant strategy is also a weakly dominant strategy, is also a very weak. So the weakly dominant strategy that we had over here, which is 555, is also a very weakly dominant strategy. And in that case, we definitely have a very weakly dominant strategy, which is both A and B are very weak. Okay, what about the other way around now? Strongly dominated strategy. Is there a strongly dominated strategy in game one?
Second matrix.
Every strategy should. Every strategy.
No, there is not. Because B and C does one.
Yes. And for the second matrix?
Yes, ma'am.
There is. Because all. So let's look at the definition of weakly, strongly dominated strategy. So a strategy SI is said to be strongly dominated if there exists another strategy SI dash belongs to SI such that the utility is this. So since in such a case we say strategy SI dash strongly dominates strategy SI. So the idea here is that we do have there exists at least one other strategy which strongly dominates this. So here we have SI dash. So this particular strategy strongly dominates the strategy which is here below. So therefore this is a strongly dominated strategy. So let's look at, so in that definition, I have that there should exist at least one other strategy. So it's said to be, strongly dominated. Is said to be strongly dominated if there exists another strategy SI dash. It's an existent. As long as there exists one other strategy such that this is less than that, strictly less than that for all possibilities. So for dominated strategies, we'll have to look for at least one strategy which strongly dominates. And then you'll have to also find what are the weakly dominated strategies and very weakly dominated strategies. So every strongly dominated strategy is also a weakly dominated strategy and a very weakly dominated strategy. That's something you have to do. And I guess now you can find both the weakly and very weakly dominated. So now what we were looking at is just strategies with respect to each of the players. Now what we need to show is what constitutes an equilibrium. What really is an equilibrium? Equilibrium is a state, is sort of a steady state where players want to play those strategies and not deviate from those strategies. Now when I say what is a strongly dominant strategy equilibrium? If there are n players and each of these players have a dominant strategy, a strongly or a weakly dominant strategy, which is given by S1 star, S2 star, Sn star, and all of them play together that particular strategy, whatever is strongly dominant for them. that particular strategy profile constitutes a strongly dominant strategy equilibrium for that particular grid. So I have a strongly dominant strategy. Since I am a rational, intelligent player, I'll probably play that. I'll definitely play that, and that is true for all the other agents. So if all the agents are playing their dominant strategy, then that particular strategy profile is called a dominant strategy equilibrium. That is what we will be ending up playing in a particular game which has a dominant strategy, which has dominant strategies for every player. Okay. For example, in the case of prisoner's dilemma, what would be a dominant strategy equilibrium? In the classic prisoner's dilemma example, where there was -2, -2, -5, -5, -1, -10, -10, -1, the other way around. So what is the dominant strategy equilibrium here? Did I get the numbers up? Just go back to the. So does this matrix have any strongly dominant strategy equilibrium? So A's strongly dominant strategy is confessed, B's strongly dominant strategy is confessed. So when both of them are confessing, that is the strongly dominant strategy equilibrium. So both of them confessing is the strongly dominant strategy equilibrium. So is there any dominant strategy, strongly, weakly, whatever, in this particular game? So how do you find that? What is the dominant strategy? Does player 1 have any dominant strategy? So how do you find dominant strategy is again restrict if the other player is, so here it is 3, here I'm getting 4. So it's always good for me to play T when the other one is playing R. In this case, it's always good for me to play T when the other one is playing L because I'm getting 2 versus 1. So T is the strongly dominated dominant strategy. Similarly, for player 2, what can you say? Does player 2 have any strongly dominant strategy? So again, you restrict for player 1. If player 1 is playing T, it is beneficial for me to play R because 3 is greater than 2. Similarly, if player 1 is playing B, it's beneficial for me to play R because 1 is strictly greater than 0. Okay? So playing R is dominant strategy for 2, playing T is dominant strategy for 1, and therefore the strongly dominant strategy equilibrium over here is T and R. Is it clear? What's a strongly dominant strategy? Okay, what about in this game? Does player 1 have any dominant strategies? What about player 2? Player 2 doesn't have any. Okay. So player 1 has a strongly dominant strategy, but player 2 doesn't really have any strongly dominant strategy. So do we have a strongly dominant strategy equilibrium over here? We don't. But what do you think would be outcome of such a game? One of the players has a strongly dominant strategy. The other doesn't have. But can you try to guess what would be an outcome? Both are intelligent players and they know what the other ones will do, etc., etc. Why will it? Okay. Why will it take L? Good. So that is one way of coming. So even if there is no dominant strategy equilibrium in a game, what you can argue is that there is at least one player who has a dominant strategy. And since he is an intelligent player, and player 2 also knows that player 1 is intelligent, so player 1 will always play the dominant strategy. And if player 1 will always play the dominant strategy, which is T, what would player 2 play? So this is not a dominant strategy equilibrium, but still this is one of the outcomes of the game. We will look at that particular outcome a bit later. Before that, okay, so we don't know, there is no dominant strategy equilibrium, but we will try to figure out what the outcome of that particular game is. But before that, I wanted to discuss a bit about dominant strategies in Brace's paradox and why in Brace's paradox, why the paradox arises. So any doubts before that about what is dominant strategies and equilibrium? So so this is the first traffic network that I have. There is a traffic that is flowing from S to T, and there are two options for all the agents who are trying to move from S to T. That is either through V or through W. So if they go from V, they are facing two roads. One is a local road and the other is a highway. No matter how much traffic is there in the highway, I always incur a cost or a delay of 1 unit time, which could be 1 hour or something like that. And if I go through the local road, there is a cost of X units, X unit of amount of time there is, where X is the fraction of the vehicles that are there on that particular road. So this question is already there in your assignment. So you might have not the assignment, the problem set. So X is essentially the fraction of agents. So let's say there are the agents who are taking this particular road, and there are total n agents. So X is essentially this particular fraction. And if this is the fraction of vehicles traveling on this road, this is the amount of delay that they'll experience on this road. Plus, there'll be a delay of 1. So this is the total delay. So it will be the utility of the agent. That will probably come. Similarly, in this particular road also, there is a X road. So now if I have to write the strategic form for this game, of course, the number of agents are n. So I have, let's say, small n number of agents. And the strategies for each of them is either to take the road V or the road W. And these are the utilities. So if I am taking the road V, and there are NV agents who are taking the road V, this is the delay that I face. So this will be my utility, minus NV by N by N minus 1. And if I'm taking the road W, and these are, and I have a certain strategy fixed for the other where they are taking NV and NW. So this is the delay that I am taking of the other. These are the utilities. So does this have any dominant strategy? What should, so is it good for any agent to take any particular road? So there are two strategies. I could either take V or W. Can you tell me if any of the roads is better for me? What would be your argument? Will depend on what the others are doing. What is the traffic in the. So for example, if I had equally distributed the number of agents in both these rows, so now I have n by 2 agents on V and n by 2 agents on W, then my utility of any agent who is taking the road above will be n by 2 by n plus 1. So this will be 1.5. Sorry, my hand. So there'll be a delay of 1.5 hours, and similarly for the other road as well, there'll be a delay of 1.5 hours. So now, if there are more number of agents on the road above, my strategy would be to go on which road?
The one and W.
The one in W. If there are more number of agents in the road below, my strategy would be to go on. Why? Because you will, if you populate the numbers, one of them will become higher because of the number of agents are equal, and this will be lower. So it's better to. There is really no dominant strategy in this particular scenario. We don't really know what to do. But if I add a I don't know, a teleporting kind of a device there that takes me directly from B to W. Now, how do we analyze this particular B? Again, let's write the, now number of agents are still 1 to n. What are my strategies now? Either I take the road B, V to T, or I take W, or I take the VW. So I have named it, you can name it any way you want, doesn't matter. So the idea is there are only 3 paths for me to take. So here there is a big gap. Now we'll have to analyze the utilities that these agents face in each of these strategies. So if the agents are taking the, if I am taking the so here, if my strategy is to take V, then the delay I'll face again is minus NV by N minus 1 because I'm taking this road. So there are the number of agents who are taking this road is NV and NV by N minus 1. And if I'm taking the road W, then it is minus NW N by, this is the same as before. But when it comes to this particular utility, my strategy would be, my utility would be this. Because here I'm facing a delay of minus NV by N because NV number of agents are taking this road. And then I have no delay here, I'm teleporting. And then I have a NW by N delay because of the number of agents who are taking this. Now, what can you tell me about these utilities? Can I claim this? That taking this utility is always greater than the utility than taking the first row. Can you see why? Because this, if I compare these two utilities, this term is the same. And what is the maximum, or what is the maximum this term can? That's the, essentially this particular term, the maximum value that this particular term can have is 1. Which is why the utility of taking this road is. Similarly, you can argue for the other. I think there's a, is there a question online? Similarly, if you look at the other, here the term is same and the maximum this value can be 1. So, which is why we'll also see that the utility for this is still greater than this. So this is it's a strongly dominant strategy for all the agents to pick this road VW. So what would everybody do? So everybody will go via that road. It's a strongly dominant strategy because of the strict inequality. You'll have to figure, I want you guys to go back and really check in all the details and how this strict inequality has come and things like that. If I change the numbers a bit, it will differ. Yes.
So everyone chooses, say, VW.
If everyone chooses VW,
Okay.
what would be the delay?
No, but then what other entities also become minus 2.
If everybody chooses VW, what is the other utility? If I deviate to the other, now everybody is choosing VW, but I decide to go to V, what would be my utility? Minus 1 by N minus 1. Clear? Let me just edit. Now, because of that, what is the total amount of delay that the agents are facing? So total time taken now, here everybody is going in this way. So here there'll be a delay of minus 1 and here there'll be a delay of minus 1. So minus 2 hours of delay. But can you come up with a strategy which is better? which will give everybody lesser delay.
You won't allow that people to
Then what should people do?
always take some SVT or SWT. Nobody uses it.
Nobody uses BW. Half of them use the top and half of them use the bottom. If half of them are using the top, then what would be the delay they'll face? Let's say nobody is going here. Half the traffic is routed here.
Minus 1.5.
Minus. We saw it last time, right? Here it will be minus half, and here it will be minus 1. Here it will be minus 1, and here it will be minus 1. So total, everybody will face a delay of only 1.5 hours. Otherwise, they are now facing a delay of 2 hours. So that's the Brazes paradox. I think one of them in the online had a question about this. So hope it's clear. So, okay. Now, how many strongly dominant strategy equilibria can a game have? So, in the above example, in all the previous examples, whenever we had a strongly dominant strategy, be it prisoner's dilemma, there was one strongly dominant strategy which was to compare. Here also there is one strongly dominant strategy which is to take the road BW. But in general, can I have more than one strongly dominant strategy in a game? By definition, you cannot really have more than one. Is it clear to everyone why? Because I need a strict inequality. I cannot have that for two different. So it's a good exercise to go and prove why there cannot be more than one strongly. How many weakly dominant strategies can a game have?
More than one.
At least one? Is it necessary to have a weakly dominant strategy? Equilibrium? You can have more than one, but it is not necessary that. So in the game that I showed,
Better than one.
so in the first game there was only one weakly dominant strategy, and both of them had. Let's say I construct a similar matrix for the column there. Why should there be at least n-1 weakly dominant strategy? And even prisoner's dilemma has only one weakly dominant strategy. So your argument is wrong. Let's just figure it out. Okay, now the question is, will a game always have a dominant strategy equilibrium? We just saw that particular example, right? Here, the row player has, or the player 1 has a strongly dominant strategy, which is to choose P. But player 2 does not really have a strongly dominant strategy because 0, 0, 1. So if player 1 plays C, it's better for me to play L. If player 1 plays B, it's better for me to play R. So there is no strongly dominant or a dominant strategy equilibria for that matter in this game. But like he mentioned, there is something else that we can do here. So we know that there is a dominant strategy for the row player. The column player doesn't have one. We don't have any dominant strategy equilibrium, but both agents are rational and intelligent, and player 2 knows that player 1 will never play the dominated strategy, that is B. B is the dominated strategy and T is the dominant strategy. So since player 2 knows that player 1 will always play T, so now player 2 will decide what it has to play, and that is play L. Therefore, TL is an equilibrium in this game. It's not a dominant strategy equilibrium. It's an iterated dominance equilibrium. So, say there is a strategy SI which is strongly dominated by some other strategy S2. So, what can we say about what can we say about the utilities here? What would you fill? If S1 is strongly dominated by some strategy. So the utility that I get from S1 will be strictly
Less than.
less than, because there is another strategy S2 which is dominating the strategy. So there is a strategy which is strongly dominated. And for weakly dominated, the greater than equality will. So in general, if S1 is weakly dominated by S2 for player I, S1 will not be played by a rational agent. So if there is a strategy that is weakly dominated by some other strategy, so I won't play the weakly dominated strategy. So now we restrict our attention to a newer game, which is I remove this particular strategy from the player I's set. And then now again I'll rebuild the matrix and think. So it may happen that after removing the game, it may lead to newer dominated strategies, and because of the assumption of rationality and common knowledge, and that's how I end up with this equilibrium, which is the iterated dominance equilibrium. That's the particular. So for example, in this game, there are 2 agents and three strategies each. So is there a dominated strategy for a player for the first player? Is there any strategy that is dominated? Weakly dominated is also fine, but I think there is a. So how will you see again? Again, restrict each of these strategies of the other player and just compare the first. So 3 is greater than 2 here.
But 3 is not better than 6.
I'm asking about a dominated strategy. Yeah, so there is a strategy wherein 3 is greater than 2 here. And if I restrict to this, 5 is greater than 3 here, and 10 is greater than 2. So there is this strategy C, which is strongly dominated by this strategy. So 2. So now what I do is, since it's a strongly dominated strategy, player 1 is not going to play that strategy. So what I can do is I'll remove that from my game. Now I have a new game. Now can you tell me, so in the previous game, did player 2 have any strongly dominated or weakly dominated strategies? Just look at player 2's protest. So the idea is so when this person is playing A, it's best for me to play X. And this person is playing B, it's best for me to play Y. And when this person is playing C, it's best for me to play Z. So there is not really a dominated strategy. Okay? But now I know that player 1 is not going to play C. So I'll remove C from this picture. Now can you tell me, is there a dominated strategy?
For player 1. So player 1.
For player 1 or for player 2, either of them. There is no dominated strategy for player 2. See clearly. You have to do all of these questions very quickly for the exam. So whenever you're looking for the column player, just fix the second. Compare this and this. So whenever will the player play X or Z? Will always play X because 4 is greater than 2, 1 is greater than 2.
No, we should look at the difference or what?
Yes, you should look at the difference and it should be at least 0. At least greater than 0 if you are looking at. So the idea is if this agent plays if the player 1 plays A, right? So it is best for me to play X because it is giving me 4 as compared to Z. And if the other player is playing B, it's better for me to play Y or X as compared to Z. So no matter what the other agent is playing, I will never play Z, right? Because there is some strategy which is giving me very higher payoff than what Z is giving. Therefore, Z is a dominated strategy for player 2. Is it clear?
Yes. Only plays right. Yes.
Why so?
Thing is, if player 1 plays A, what would you pick if you were player 2?
I mean, everywhere a player one is having more.
No. Look, now you are player 2, okay? So you have to only look at your utilities, which is the second,
Correct.
right? So if
Second
you
element
play,
in the tuple.
yeah, if player 1 is playing only A, so you restrict yourself to this row. If you play X, you're getting 4. If you play Y, you're getting 3. If you play Z, you're getting 2. Will you pick Z?
I'll take X more.
You will take X. That's correct. That's correct. You will never pick Z. Similarly, if the other player is playing B, if you play X, you're getting 1. If you play Y, you're getting 6.
Why?
And if you play Z, you're getting 0. Will you pick Z?
No.
No. So in this game, you will never pick Z because the other player has only 2 options, right?
Okay. So Z is ruled out.
Yeah, therefore Z is a dominated strategy.
Okay, dominated means it will never be in the consideration.
Exactly. So now player 1 knows that player 2 is never going to pick Z. So you can remove Z from the picture. And now you have an even lesser matrix to analyze. Now, are there any dominated strategies?
Player one dominated this week.
Huh.
Ma'am, we're still calculating for player 2, is it?
No, you have to find any dominated strategy for any player, because even if any of the player has one dominated strategy, they are not going to play that. You can remove that from your game, right?
Yeah.
So if let's say you're calculating for the column player, does the column player have any dominated strategy in this game?
No.
No, correct. Does the row player have any dominated strategy?
Let me think.
Yes, it's B. So if the other player is playing X, it's better for me to play A because 10 is greater than 0. If the other player is playing Y, it's better for me to play A again. So I'll never play B. So B is a strongly dominated strategy in this case. So I can remove that. And now it's easy to see what's a strongly dominated strategy because player 2 either gets 4 or 3. So player 2 will always stick with X. So AX is the equilibrium.
No. So can you explain this equilibrium state now? I mean, we eliminated Z and B.
So now we have eliminated B, right?
Yes.
So
And
now
we
we
are
are
left
left
with
with
this.
this game. Now in this game, can you tell me what player 2 will do? So player 1 has only one strategy. So player 1 is always going to play A. But
Correct.
what will play, if 2 knows that player 1 is always going to play A, what would player 2 play?
X.
X. So finally, in this big matrix that you had seen, we eliminated the dominated strategies because players are smart. They are not going to
Player
play
one is playing A,
yes.
and this is that player 2 will be choosing X only because it has a higher value for player 2. But
Yes.
the difference is 6. I don't know what that difference signifies.
What difference is 6 here?
10 minus 4 is 6.
No. We are not worried about that difference. So we are worried about the difference between these two. If 4 is greater than 3, I'm going to stick with 4. There's no difference of these two. So there is no way I will compare utilities across players because that doesn't really mean. I'm just looking for my own utility. So I'll compare my own utility when I'm playing some other strategy.
In that
So
way, second Y will become redundant.
Sorry?
In that case, player 2 will not be choosing y, no, column y.
Yeah, that is what I am also trying to say. Player 2 will not be choosing Y. Player 2 will only choose X. That is why AX is the equilibrium state. So both the players will only play these strategies. Player 1 will play A and player 2 will play
Then-
X.
Then why don't we further reduce it to like only one element matrix?
Why don't we?
Further reduce it matrix like
Yes, sorry. Yeah, so ideally the end of the game is just one matrix. 1 and 2 and X and A. Then come out. Yeah, this is the final matrix.
no, but in that case, 2 is always going to lose. No,
Why will 2 win?
lose.
No, 10 and 4 are not. So there is a certain strategy when so the idea is 10 is the utility of 1 and 2 is the 4 is the utility of 2. They cannot be compared. This doesn't mean that one is getting more and I am getting less. This just means, so the utilities are not comparable across agents.
Okay, so okay. So this simply signifies that both are looking at the maximum benefit for themselves.
Exactly.
Okay.
They define their own utilities and they select their strategies, whichever is good for them. So I may be, this 10 could be 10,000 and this could be 0.004, doesn't matter. Right. It's his utility minus mine. This is also an important point. So the utilities are not comparable across agents. So when we are in utility theory, we are eliciting utilities from these agents, right? So one agent could be reporting in thousands and one other agent could be reporting in the range of 0 to 1, right?
Correct.
They could do that and it's fine because it's their own conventions that they are following.
One question about maybe asking that if there is a 5 instead of 3,
If there is a 5 here instead of 3, yeah, in that case,
what should be the determining of how we can get it?
if it is 5 instead of 3, then it will be AY, right?
But the A should choose X. A should choose first. Okay, got it.
Okay.
Ma'am, can you repeat that answer again? The answer you gave just now.
So if here instead of 3, I had 5. Okay, this slide is now. How do I get rid of all of this?
I think you can click. There's an eraser option. Yeah.
Yeah,
you can just erase
anything
it.
more than 4 in the y.
Yeah, anything more than 4. Yeah, right. Anything more than 4, you will just choose the other, right? If it was exactly 4, then both of them are equal. Playing both of them are equally good for me, for the player 2. So both of these will be dominant strategy equivalent. Iterated dominant strategy.
Yeah, so if x is 10 4 and y is 5 or whatever and more than 4, then we'll have equilibrium state will have both the
A and
columns
Y.
x and y.
A and Y, not X. A and Y. If it is, let's say, anything more than 4,
Okay.
then the equilibrium will always consist of the strategy of all the players, the strategy profile. So A for the player 1 and Y for the player 2.
Okay, but in AY, the value of, utility for player 1 is less than compared to AX.
Yeah, but why will player 2 play X? He doesn't care about player 1, right? Yes.
Oh, it's just it got reversed in that sense.
Yeah. Clear all doubts?
Yes, ma'am.
One more example, little.
You want one more example? Okay, then.
Yeah, this was clear, but one more example may throw some more questions.
Okay, then in that case, I can open the problem sets, I guess. I have one example there. And that will also be interesting because.
And ma'am, maybe after this class, the camera installed in the classroom can focus more on the display board. That will give.
But am I not sharing the screen?
You are sharing the screen, but when you are explaining on the display board, that is much more
Oh,
better.
the
Right now the view angle is covering 50% area, which includes the display board, and 50% area is like behind. I mean, besides the board and all. Not this one, ma'am. The camera installed in the classroom. That you can do it later, not now.
What about
Yeah.
now?
Yes. A little more. Yeah, much better. Thank you.
Okay, great. So, so in this problem set, I have this question. Can you tell me what would be the? Let's go with problem 1.3. I hope this is very simple. Okay, what would be the outcome of this game? Is there any dominated? It's not visible, yeah.
Yeah, it's visible.
Okay, these are the students in the back. Is there any weakly dominated strategy? Okay, for player 1.
Player 1, if we fix the row A, then X and Y will be weakly dominated, no?
So for player 1, if the other player is playing X, he'll play A. Okay, here I can't write. If the other player is playing Y, he's indifferent, but the other player is playing Z, then he'll play B. So there is no dominated or weakly dominated. But for player 2, is Z a weakly dominated strategy? Weakly or weakly? So if player 1 is playing A, Y is giving me better than Z. And if 1 is playing B, Y is giving me at least as much as Z. So there is no reason why I'll play Z, because there is one more strategy which sort of weakly dominates. So now if I have to write the next matrix, what column will I remove?
Z will remove.
Z you will remove. Now imagine Z is not there. And now tell me is there any more dominated strategies and things?
X, column 2 again is column Y instead of column X. Always.
We will choose Y.
What about player 1? Just forget about Z. Look at player 1's strategies. Okay. There are two things now you can do. Either you favor player 1 and say, look, player 1 has a weakly dominated strategy, which is B, because A is always giving me better than what B is if I remove the third column. So either I'll reduce the matrix by considering one row that is A and 2 columns X, Y, or what I could say is that player 2 has one more dominated strategy, which is X, and Y is dominating it. So now I can have A, B, and Y. There are two ways in which I can sort of go ahead with the iterated domination. I can remove B. If I remove B, what would be my equilibrium? And if I remove Y, what would be my equilibrium? Will it be same or different? Can you check?
Yes, ma'am, both are possible.
So if I remove, I remove B, X and Y both are equilibrium.
Same thing.
Yeah, same thing. So what would be player one's strategy in that case? Play A, but player two could be playing X or Y, right? Doesn't matter. Now, if I remove if I remove X and keep A and B, what would player Y? What would player one play then?
AB.
But why has more?
Why does I don't care about Y's outcome? I only care about my own outcome. Okay, don't think that nobody is going to think about the other player. Okay, keep that in mind. Don't in the exam. Don't go and write B and Y is the A or exactly. So player. So these are very two different kinds of. So both are equilibrium. Both are iterated dominance equilibrium, but they are very different. You see. So in one, player one is going to play A, and player two can play either X or Y, and in the other, player one can play either A or B, but player two will always. But in practice, what will they really do? Okay, so one more. That's the example for iterated dominance. It's 11.
Yeah, but
I
suppose
hope it's a bit clear.
suppose, but going by the utility, if player one is playing, I mean, if player two is only playing Y, that will give better utilities for player one, no? In either if it is he's playing
For
A or
player
B.
one or for player two?
When player two is playing Y only,
Ah,
then player one will be playing A or B, and in both the cases it will get utility one,
fine.
which is kind of better than have utility 0, possibility for utility 0.
But why will it ever get 0?
Acha, okay, it will not go there. Correct. Yeah, so in that case, player one will always have utility A only. One only, yes.
Okay, so we have learned two concepts of equilibrium. One is dominant strategy, equilibrium. But if dominant strategy, equilibrium doesn't exist, you look for iterated dominance. That could be one of the outcomes of the game. But can there be games when neither exists? Is it always guaranteed to find? Are you always guaranteed to find a game where either there is a dominant strategy equilibrium or there is an iterated dominance? So, for example, in this game, can you tell me what would be the dominant strategy equilibrium or iterated dominance outcome? So, for iterated dominance, what is the requirement? At least one of the player has to have a weakly dominated strategy. So now what you have to look for, does any of the player have any weakly dominated strategy? So no, right? I hope it's clear that there is no. If the other player plays C, I'll play C. If the other player plays R, I'll play R. So this is a coordination game. Both of them like to do things together. So if the other, so if player one is playing C, I would like to play C. If the other player is playing R, I would. Therefore, there is no weakly dominated strategy for any of the. So you cannot reduce this matrix. You cannot find equilibrium. So what would you do in this case? So this is so that's when we will that's where for things like that, what we have is something called a Nash equilibrium that is defined, and we'll be talking about Nash equilibrium in a bit. But before I move to that, I want to talk about how strongly dominant strategies or iterated dominant strategies are very nice, because people are able to really figure these dominant strategies very quickly. So I know I have a dominant strategy, so I'm going to play that, and it's easy for us to build systems where people have dominated strategies, like dominant strategies, so that people follow that. And when people follow that, as a system designer, I get the outcome that I want when people follow these strategies. So that's the idea. So we would like to see in auctions how dominant strategies play an important role. So dominant strategies are good and relatively easy. People don't do it still, but they are relatively easy for intelligent people to follow. So we would want to see how this guides our design of systems. So now we'll be moving to the setting of auctions. So what is, I'm sure people do watch IPL auctions and things like that. So I know, I believe you are a bit familiar about what auctions are. So what we are looking at is something called a sealed bid auctions. So you have one particular item which is for sale, and let's say there are 4 agents. Now these 4 agents have certain value for these items. What do I mean by value? They could sell this item and probably get some amount of money by selling. Now each of these agents have, let's say, 10, 8, 6, 4 corresponding valuations. And this particular valuation is private information. This is what they know about it. The others, or even the auction designer, the one who has designed the auction, does not know what these values are. So which is why there is this entire process of sealed bid. For the auction designer, the aim is to give this item to the person who can use it the most, or who gets the most value out of it. These are the true values that these agents have. And since agent 1 can actually take this item and make a profit of 10, which is a very high number, the auctioneer would want this particular item to go to agent 1. That's the goal. But the auctioneer doesn't really know what these values are, which is why it cannot just directly go and give the item. So it conducts an auction. And when we conduct an auction, what we want the agents to do is to bid. And ideally, it's a sealed bid auction. The bids are not visible to the other. So all of them will write what their bids are in an envelope, and then they'll submit the envelope to the auction at the same time. It's not a sequential. And now, so this defines what our strategies are. So my strategies are the number of the bid that I submit. Now I could submit a bid which is starting from 0 up to infinite, any number. So my strategy space is a continuous space, and infinite strategies I have, which would be 0 to infinity. All of these agents have them. Okay? These are my strategies. So I'll sample a particular strategy or a bid from the set, and I'll submit it. So agent 1 submits B1, B2, B3, B4, and there is no need whatsoever for you to submit for B1 to be equal to B or B2 to be. There is it's not necessary that you submit the actual value. You can submit whatever number. Now the auctioneer creates a game. Essentially, the rules of the game are that based on these bids, I'll decide who this item is going to go to. That is called allocation. What is allocation? Allocation is who is going to get the particular item. Now that is represented by this variable yi. Now yi is 1. So essentially, in words, if I have to say, the auctioneer is going to allocate the item to the highest bidder. How do I denote that? So whenever an agent's bid is higher than the others, yi will be 1 for that particular agent. And let's say both of these agents submit a bid of, so let's say the bids are something like this. 10, 10, 5, 3. So the idea is either 1 or 2 can get, but now I'm assigning the lowest index. So the highest bidder is both 1 and 2, but I will allocate the item to 1 because that's how I sort of made the system. I wanted the lowest index one to win. The index as in the agent number 1 and 2. For the others, they are not going to get the good. It's an indivisible good. There's only one item, only one can get. So the winner gets it and the others go and be happy. So this is the allocation. So any auction consists of 2 parts. One is the allocation part, who is going to get the item. And the other is the payment part. How much are they going to pay? Now there are many kinds of auctions. But there are 2 auctions that I'm going to describe today. One is the first price auction. What is first price auction? The winner will pay the amount that the winner has bid. Right? So essentially, So essentially that bid is the maximum bid of all the agents, right? So the winner is going to pay the maximum bid. It's clear, right? Maximum of all the agents. So Pi is equal to Yi dot max J feature. Now, whenever Yi is 1, that means I'm the winner. I'm going to pay the maximum bid or my bid because I'm the highest bidder. That's my payment. If Yi is 0, so for every other agent who is not getting anything, they are going to pay nothing. Pi is equal to 0 because Yi is equal to the Pi is equal to the maximum bid for the person who is winning the auction or who is getting allocated, and the others are not paying anything. In second price auction, there is a slight change. What I'll say is now the winner is again only going to pay, but he is not going to pay the highest bid. He is going to pay the second highest. So if I remove myself, I am the highest bidder. If I remove myself, whatever is the second highest, I'm going to pay. So first price auction, there is only one winner since one item. The winner is the highest bidder is going to get the item, no matter what the auction is. In both the first price auction and second price auction, the highest bidder with the lowest index is going to get the item. In first price auction, they're going to pay the maximum bid, which is their own bid. And in the second price auction, they're going to pay the second highest. Any doubts in the setup? Is it all clear?
Clear.
Okay. So this is known to the public. What all in this board is known to the public? The valuations are, I know, all the agents know their own valuations. They do not know the others' valuation. The bids, I know my bid, I don't know the others. So that's the information. The allocation and the payment is known to the agents. They know this is the allocation rule and this is the payment. Now, this is the common public knowledge. This is how the game is going to be conducted. Now, okay. So in this, for example, in this game, if I have to conduct first prize auction, who is going to be the winner? Third agent, because they have submitted 3, 2, 6, 4. The highest bid is third. And how much is the third agent going to pay? 6. Oh, okay, please. Okay. So how do I define my utility? The utility is, if I'm going to win, I'm going to get the value of the good, which is 6, but I have to pay. And since this is a first price auction, I'm going to pay 6. So my utility is 0. Is it clear? So no? Okay. So since U3 is the winner, Y3 will be what? Y3, okay, Y3 is allocation. Y3 is 1 if for the winner. And I'm saying that the highest bidder is the winner. He bid the highest. So for him, the Y3 is 1. V3 is the value that, because the winner is getting the item, he's going to derive a value out of that item, right? And the value that it derives is 6. Now he's got to pay some because first price auction. Since it's a first price auction, he's going to pay his bid, which is 6. So 1 times 6 minus 6. What would be the utilities of the others? It will simply be 0 because Y is 0 for the others. Nobody is going to get.
When Y3 is bidding and user 3 knows the value as 6.
Yes.
Behaving rationally, his bidding will be less than 6 only.
Very good, very good. We'll come to that. We'll come to what his strategy should be. I'm just describing what the auction will be. What are utilities in this auction? What are just setting up the form. So I'll come to that. Okay, what if I do a second price auction in this? What would be the utility? Again, the highest bidder is winning. So Y3 is again 1. V3 is the value that it gets doesn't change, 6. But the payment it makes is changing because now it has to pay the second highest bid. And the second highest bid, apart from minus the highest, so I remove myself, and the second highest is 4. So 6 minus 4, So this is the utility that the third agent will get, and the rest will anyway get 0 because they are not getting it. So now are the two options clear and the setup clear? Okay, now let's think of what the strategy is. If I say this is the first price auction, this is what I can see. I know what a first price auction is. All the players know what a first price auction is. I know my value. Let's say my value is 5. So what should I bid?
Should be less than 5.
But there's a chance that you won't win. Okay, so if you bid less than 5, what will happen? Either you may lose. When will you lose? When others are bidding higher. When there is at least one other agent who is bidding higher, you may lose. But if you bid, let's say you bid less than 5 and the others have bidded this 3, 2, 1, then you will win, right? And you will get a utility of 1. Why? Because your value is 5 and you are paying your bid because yours is the highest bid. So your utility is 5. Had you been truthful, had you gave your exact bid, which is 5, you would have gotten a strictly lesser utility. So if you bid less, there is a possibility that you will get more utility than had you given your true value. So, but how much less should you pay? Should you bid? Can you figure that out? Isn't it tough? Because you don't know what the others are going to bid. Right? Should maybe the other bids are like 4, something like that. Maybe then you should have bidded actually 4.1 and not 4. By how less you should bid is not very clear. Right? There is no clear-cut strategy. Will you bid more?
Then we have negative.
Then, so if you bid more, you may lose. There might be still others who are bidding even more. In that case, it's fine. You get 0. But you may win and then you'll have to pay 5, right? Or at least more than 5. But you get only a value of 5. So there is a chance that you get negative utility. So it's sort of a dominated strategy. Right? Bidding more is sort of a dominated strategy. So you always bid less, but you still don't know how less. What your exact strategy is not. Right. Okay, so is this clear?
In real market scenario, one may bid B can be greater than V if the intent is to at any cost win the bid and remove the competition.
No, but if at any cost they are going to get it, then they'll have to pay their bid, right?
Yeah, that is okay. I'm saying in the real world scenario, people do like that.
People do like, but
and companies do behave like that.
But I think in most of the real world scenarios, don't people have second price options? I mean, I'm asking. I thought IPL was second price option. Is IPL a first price option? I'm not sure. You have to verify. I think all the English auctions, and I think IPL is in English. All the English auctions are second price auctions, and I think IPL is.
When they bid more money, that's what they show.
So the bidding more will make you the winner, right? But how much you pay?
They should scarce with this much. I don't know if they play this.
You don't. So in Google auctions, I think it was second price, but it's slightly different than the second price I'm explaining. Okay, these auctions are not the optimal or the best option. There are many drawbacks which I will discuss. But now what I'm trying to show is that how do I model auctions in a strategic form, in a game form? What are dominated strategies in this particular auction? And so I know that I should bid less because bidding more is a dominated strategy. And if I bid less, but I don't really know by how much, it's not really clear what my strategy should be even in this case. Now let's look at the second price options. So if, again the same, I don't really know what the values of the other agents are or the bids are. I know my value and what should I bid. I also know the fact that it's a second price option. So I might bid less and I may lose and have 0 utility. But if I bid less and let's say I encounter the same bid profile as before, 4, 3, 2, 1, what would be my utility? I'll win. What would be my value? I'll get a value of 5. And how much do I pay now? The second highest. Right? So I get the utility, I pay 3. And notice that my payment is not dependent on my bid. I'm bidding in the previous case, in the first price auction, the payment was my bid if I bid. Right? It was dependent on my bid. Here, the payment is not dependent on my bid. So my utility is going to be 3. If I had bid 5, my actual value, I would still get the same utility, right? Why? Because I still derive the same value because I'm still the highest bidder, and I'll have to pay the second highest, which is still 3. It's not dependent on what my bid. So truthful bidding is at least as good as what you can get whenever you bid less. Even if you bid truthfully, you will still get that maximum utility. So sort of a weakly dominant in this case whenever you're bidding. Now let's think of the other way around. When you're bidding more. So if you bid more, you may still lose and have no utility. But it may happen that you have bidded just high enough, right? Where you are winning. And now your utility, what would be your utility in this case? Your utility is whatever value you're getting and the second highest, 5 minus 4, 1. And if you had bid truthfully also, you would still get that. It doesn't matter. If you bid really high, right, and there are bids which are higher than your value, then you might end up getting a negative because you're paying the second highest and second highest is still more than your value. So here also, what is the best thing for you to do? Bidding truthfully. Because the highest that is not a strongly dominant. Why? Because you can bid something else and still get that, but truthful bidding will at least get it. For sure. So if you want to bid, so no matter what, there is a weakly dominant strategy which is truthful bid. Is it clear? So in first price auction, through this analysis, we cannot really come up with any dominant strategy of sorts. Then of course you will always bid less than value. But how less and what is the exact bid, not known. But in second price auction, we are ensuring that they bid their true value. Because that's a weakly dominant strategy. So now people are clear in their heads. If it's a second price auction, I cannot really do anything better than bidding my true value. I might as well just. So that's how you ask agents to, if agents are intelligent and smart to figure this out, then they'll just not put a lot of effort into deciding what to do. It's better. That's a good question. Ideally, it's better for auctioneers if you want the agents to have a clear-cut strategy. But it is shown that they are not revenue optimal. If you want to earn a lot of money by making people bid more and more and more, and there is something called, there are revenue optimal auctions, wherein you have a second price and a threshold value. You start with the amount of price. You give your own bid. So you start with this particular value. If there is anybody who is bidding more than this, and then we'll conduct the second auction. If anybody is bidding less than that value, then you will just scrap. Nobody is bidding. So that will ensure that you earn a higher revenue. So depending on what your objective is. So this auction will definitely guarantee one thing. And what is that one thing? The agent who values the good most will. Because agents in this case, the best strategy for them is to bid truthfully. And if they bid truthfully, I'll really know what their values for the items. And now what I can do, I can actually go and give that particular item to the person who values it the most. So this is called welfare optimal auction. So when I want to maximize social welfare or maximize the value that the agents are going to derive out of this item, then second price auction is one such auction which is going to maximize social. In first price auction, we don't really know if people will really bid their true value. They might reduce it and then the ordering might go. So that we cannot really say if it will be a welfare optimization. This will be a welfare optimization because of the fact that there are weakly dominant strategies. But the sad part is you cannot always have weakly dominant strategies because there are games which do not have weakly dominant strategies. Can you always build one? Probably not. So what are the other kinds of equilibrium that we can look for? Let's see. Next 5, maybe 10 minutes of the lecture. And okay, so any doubts, any questions? Actually, these people are, there are decent people and they figure this out. They will, otherwise, they are going to be at a loss. So just look at now we are trying to so when these dominant strategies or even iterated dominance may not exist, right? In that case, what can we do? So for that, first let us try to see some properties that these equilibriums satisfy, right? And then based on that, we will see how we can come up with new versions of it. So if you look at this iterated dominance example that I had given before, maybe AX was the dominant strategy. Yeah, AX was the iterated dominant strategy. If you look at it, I think you had already described this property before. So if I want to analyze A of X a bit more carefully, so let's say player 1 commits that I'll play A. There is a dominant strategy X. And player 1 commits that I play A. If player 1 always plays A, then what would player 2 do? So if player 1 always commits and says I'll play A, then player 2 will always play X. Because 4 is greater than 3. Now, if I say if player 2 commits to X, what would player 1 do? Will always. So if there is a sort of a understanding, so if you play A, I'll always play X, and if I play X, you'll always play A. But so there is this nice property about AX. Let's verify if that is true for BY, some other random strategy I have, B and Y. Will it be true for B and Y? If player 2 plays Y, what will player A play? A. Okay, A. And if we have, and if player 1 plays B, what will player 2 play? Y. So if player 1 plays B, player 2 will play Y. But if player 2 plays Y, 1 will not play. One will shift. One will deviate from this strategy. So this strategy is not keeping them together. If I play B, you'll play Y. But if you play Y, I won't play. So this is not an equilibrium state. People will want to deviate. So A will want to definitely deviate from this. But that is not true for this AX. If you play X, I'll play A. If I play A, you'll play X. They'll want to sort of keep playing. So that's the property that we are looking for in an equilibrium, where people would not want to deviate, given that the others are committing the strategies from where they don't want to. Now, this is true. This property is true for any iterated dominance equilibrium. This property will be satisfied. Similarly, in Prisoner's dilemma, I have this strongly dominant strategy, which is CC. If you analyze this, it will still be true here. If the other player plays C, it's best for me to play C. If I play C, it's also best for the other player to play C. Okay, so this is a strategy that will keep them together. But that's not true for, let's say, NC or the other. So if player B plays NC, what will player 1 play? C. And if player 1 plays NC, player B will again. It's not a sort of an equal. People will deviate from this. So in coordination game, what would be that strategy which will prevent people from deviating? Like a strategy, if I play this, you will play that. If you play that, I'll play this. So what would be that strategy? What would be that? And so if I play C,
The other plays C.
the other will play C. If the other plays C, what will I play? So if let's just go through it. If I play C, player 2 will play C because he is getting higher equity. Now if player 2 plays C, I am also going to play C because so C, C seems to be one of those nice strategies where people won't be. Let's look at R. If I play R, what would be the other agent strategy? Right, 2 is greater than 0. Now, if the other agent is playing R, what would be my strategy? So even R, satisfies that. Both coordinate in a coordination game. We like to do things together. That is either go to class or go to room. So even if both of us are going to class, none of us want to deviate. Or if both of us are relaxing at room, none of us want to deviate from that. So these sort of equilibrium, this is the equilibrium which is termed as the Nash equilibrium, wherein people do not want to deviate from this particular strategy. And if you can verify that this is not true for the other. So what you have to do is, if I fix the other player's strategy, this should be my best response. If my best response is fixed, then the other's best response should also be this. Only then this is an equilibrium. This is the Nash. So is there any dominance? So we already seen that there was no dominance strategy or iterated dominance equilibrium. So both there are two equilibriums in this case, the CC and R. So this particular notion of equilibrium was given by John Nash. I think it was published in his PhD thesis in 1950 at Princeton. So in this particular equilibrium, people are playing some fixed strategies, either C or R, but he also talks about something called mixed strategies, and that's probably his most renowned contribution. But the concept of equilibrium, this sort of equilibrium, was first given by him. And there is this movie called A Beautiful Mind. I think a lot of you must be familiar with it. In that movie, actually, in one particular scene, they try to describe what Nash equilibrium is, and I feel that is wrong. So maybe it will be good for you guys to go and check. I think there is a lot of debate about that particular scene in the forums online. You can see their arguments and figure out for yourself if that really is a Nash equilibrium, what he was claiming. Or it's probably a bar scene or something. I don't remember it now. Okay. So the formal definition of Nash equilibrium. So now this is a pure strategy Nash equilibrium. It will be clear why it is called pure strategies, maybe 2 lectures down the line. But for now, you remember that there is F1 up to Sn star is a pure strategy Nash equilibrium if when all the others commit to Si, S minus I star, for me, Si star is the strategy that gives me the maximum utility. So when I play Si star, and if others are fixed and they are playing their Nash equilibrium strategies, quote unquote, S minus I star. So it is best response for me to play the Nash equilibrium strategy, which is the Si star. So how is this definition different from dominant strategies, equilibrium? What changes? So let's say SI star was my dominant strategy. Okay. So UI, if SI star was my dominant strategy, then UI SI star would be greater, since it's a dominant strategy, it would be greater than any other strategy. But there is a difference from the Nash equilibrium. What would be the difference? Strongly dominant or normal dominant, whatever. Exactly. So here, what I'm doing is I'm fixing the other strategy. So for me, it's best to play Nash equilibrium strategy only if others are playing the Nash. If others stick to that strategy, it's good for me to stick to this. But a dominant strategy is one that no matter what they are playing, it is always good for me to play. Right? So here, instead of S minus I star, I'll just have an S minus. So for all possible strategies that the others could pick, playing SI star is always good for us. This is a very strong notion. So if is a dominant strategy equilibrium also a Nash equilibrium? I will go there later. But yeah. So the idea is, no matter what the others are playing, it is good for me to play the SI star. But in Nash equilibrium, we don't claim that much. We don't say that. What we say is, if others are fixing their strategies to some S minus I star, it is good for me to play SI star. And that is true for all I. So there will be for all I, this will be. This is the proper definition. Yeah, because for every SI, S minus I, if it is greater, then for this it will be definitely greater, right? So for every dominant strategy also. This is the formal definition. Or you can also write it like this. S minus I is the I star is the maximizing, the utility maximizing or the best response strategy when others are playing S minus I. So can a game have a dominant strategy and a Nash equilibrium strategy both? Can you give me an example of a game like that? I mean, Matrix. I want a game where there is a dominant strategy and there's also a Nash equilibrium, a dominant strategy equilibrium and a Nash. So another strategy which is Nash equilibrium but not dominant strategy. Can you try to come up with a game like that? Matrix. So you know what is Nash equilibrium, you know what is dominant strategy. You tell me it's not possible or just dominant, not strongly. So people online, do you have any doubts regarding the definition of Nash equilibrium and any other questions or doubts? What is the Prisoner's Dilemma has one strongly dominant strategy. That's also, I'm asking about one more strategy which is not dominant strategy but is Nash. Any other doubts, questions in the definition, notation?
Any coordination can be a
There is no dominant strategy there, no, in the coordination. But there is a Nash equilibrium. I want you to tell me again where there are both. One is not the other. Nash equilibrium, there is a strategy which is, there's an equilibrium which is Nash equilibrium but not dominant strategy. That is possible. Every dominant strategy equilibrium is a Nash equilibrium, but is every Nash equilibrium a dominant strategy equilibrium? That clear? So I want you to tell me again where there is one dominant strategy equilibrium and one Nash equilibrium which is not a dominant strategy.
Then Nash equilibrium, like a subset of something is dominant.
What does that mean? Yes, it's not normal. It's possible. Right. Can you give me a game where okay.
Let's say that there is a bottom, it is one. One step that has so one is the other one. The one above that.
Okay.
And then the first one is okay. And then corporate identity is like bigger.
And what about you?
Two.
2, 2. Okay. Let's analyze this. What would be a dominant strategy here for the player 1? I don't know. We'll check. So if this, what is the dominant strategy for player 1? So 2, 2. So sorry, I should give A, B, and player 2 has X and Y. So the dominant strategy, both are equal, right? A or B. There's no any. What about 2? They are equal. So all of them are equilibrium. And this. So
There's no dominated one.
there's no dominated. Both are weakly dominant. Because 2, 1, 2, 1. Did I miss out? So all are dominant strategies here. But I want you to tell me one Nash equilibrium which is not dominant. So since all are dominant, then I can't find that. Okay. Example. This one, 3, 3. Three, 2 is the dominant strategy. A. So for the player 1, is there any dominant strategy? A. A is the dominant strategy. And what about player 2? So AX is a dominant strategy equilibrium. What is the Nash equilibrium in this game? AX is definitely a Nash equilibrium in this game. Is there any other Nash equilibrium? If player 1 plays B, what would player 2 play? Either X or Y, doesn't matter. If player 2, let's say, plays X, what would player 1 play? A. So B is out of picture. So if player 2 plays Y, what would player 1 play? Doesn't matter. So definitely this is a Nash equilibrium. 1, 1. Because if player player 1 plays B, player 2 can play Y. If player 2 plays Y, player 1 can play B. What are the other? So this is one game where there is a dominant strategy and there is a Nash equilibrium which is not a dominant strategy. Are there any other Nash equilibriums in this game?
When players play Y, two players Y can play A or B.
Right.
So
But if I play A, what would player 2 play?
I play A, player play
X. But so is AY a Nash equilibrium?
Y is also naturally should be.
Why? So let's analyze A and B. If I play A, player 2 will play
X.
X.
Okay, so that's what I am. That's
Why BY is Nash equilibrium? Okay.
is Y. Y A one
Can play B, right? Why not? Why should he not play B?
maybe suppose the one.
So this is a game where there is a dominant strategy and a Nash equilibrium that's not a dominant strategy. I hope it's clear what is dominant strategy, what is Nash equilibrium, what is yes question. So how do we identify Nash equilibrium strategy where we don't know S minus I star? I didn't understand your question. What would that mean? So if I don't know S minus I star,
Basically, star is commitment of the other player,
right?
and I don't know about the commitment, what they are going to commit.
Yeah, so it may happen that there are two different Nash equilibriums and they might commit to different things. That is possible. So we don't really know what they will do. But if what I am claiming is if it's a Nash equilibrium, that means if they commit to that strategy which is Nash equilibrium, I will get the best out of this. In practice, what they will do, nobody knows, because Nash equilibrium is not really a unique solution. They might do different, they might switch between their different strategies which are Nash equilibriums, and in that case you don't know. Or we will learn what there's a mixed notion as well, wherein you can mix your strategies and things like that. But here I'm just talking about the definition of what a Nash equilibrium. If they commit to that strategy, it is good for me to commit to mine, and likewise for everybody, then it's a equilibrium. I guess this will be clearer as we go when we talk about mixed strategies and things like that.
Can we actually figure out that game is actually? I mean, we
Okay. Perfect information of the other. So, in all the games that we saw now, Prisoner's Dilemma, is it a perfect information? Is it a perfect information? So all these games that we discussed are imperfect. Okay. So next class we will see, but is Nash equilibrium always guaranteed to exist? We don't know. We'll see that next class. Can we always find the Nash equilibrium? Or what are the games? There are some games called matrix games wherein we can always find Nash equilibriums. And we'll also learn some more nice properties about Nash in the next class. Thank you everyone for attending. See you in the next class. I have some problems with some no Nash equilibrium questions, but feel free to answer those. And if you have any doubts, we can take it up in the next class. Okay? Thank you. Thank you. Let me stop the recording.